Hi everyone. For our last video, I would like to dig into that problem that we've been talking about for the last few videos, which is our sheet of charge. If we've got a sheet with a uniform charge distributed among it, that's got an area of A, I'd like to try to find the electric field, E, at some distance above the plate. Let's say it's got a distance of D above the surface. And the way that we're going to do that is we're going to follow the 6 steps that I mentioned in the last video and solve using our Gauss's law equation. You may have noticed that we've already actually done the first 3 steps in the previous videos. We, number 1, drew our electric fields, including the weird edge effects. We tried to draw a Gaussian surface, step number 2, and failed miserably when we noticed that the electric fields pierced that box at all different kinds of angles, and therefore we weren't able to use our simplified flux equation. That led us to drawing a smaller box that was able to obey our criteria so that we could have an electric field that's perpendicular to the surfaces or parallel to the surfaces, and now we're able to move forward with our Gauss's law problem. Step 4 is to find the total charge enclosed within our Gaussian surface. This is our plane, and this is our Gaussian surface once again. And so we need to find the total charge enclosed within that space. You might already start to notice a problem brewing though, so we actually don't know the size of our box. We could define it using numbers, but let's be good physicists and use algebra to our advantage. Let's define it arbitrarily as some kind of area vector A. And let's say this cube has an area A all around it, and it goes right through our point some distance away D. So now we need to find the charge enclosed within our small area A. And the way that we're going to do that, I'm going to show you a trick involving something called the charge per unit area, which is a sigma in this case. And it's just what it sounds like. It's the total charge divided by the total area of our surface. If we know the charge per unit area of our whole surface, we can multiply that by the little area that we're digging into and figure out the total charge enclosed. So in this case, charge enclosed is equal to sigma, our charge per unit area, times the small area that we're trying to dig into. Or another way of saying that would be Q enclosed is equal to sigma, which is Q over A, times our little area A. And yeah, we don't know how big that area is yet, but let's just keep plugging ahead, and we can plug this into our equation, and hopefully things will cancel out and we'll figure it out in the future. Now on to step 5. Let's look at the surface and find the flux through each of the different surfaces. I'm going to point us to this diagram over here. And remember that the electric fields were going up and down through that surface. So let me blow out the side surface here, and let's look at the electric field going through that side surface. It was all up and all down, but the area vector is pointed out this way. So you'll notice that in this case, the angle between the electric field and the area vector is 90 degrees. So we're looking at the cosine of 90 degrees, which is equal to 0. So that means that we can pretty much completely disregard this surface. There's no flux lines going through this surface. And therefore the flux through the side surface, and indeed the left side and the front and back, all have 0 flux going through it. So which surfaces are left to have flux going through it? Well, the top surface is a good one. Here's our top surface, and remember, actually the area vector in this case is little a, and our electric field lines going through the top surface is also going up here. So in this case, the angle between them is 0 degrees, and remember the cosine of 0 is equal to 1. So now we can write the flux through the top surface is equal to E times little a. We have to do the same thing for the bottom surface, and I can draw a similar picture for the bottom surface, but the end result is that our bottom surface is going to have a flux of EA as well. So that means we just need to total the 2 up, and we would get 2EA for the flux going through our Gaussian surface. And that we can plug right into here, and we can move on to step 6, which is to solve our problem algebraically to find out what the electric field is at some distance above the surface. Let's plug in both things. We're going to say 2EA is equal to, charge enclosed, we're going to plug that in as well, Q over A times little a, all over epsilon naught. All right, let's do the easy thing first. Remember that arbitrary area at little a? Cancels right on out. So we were actually able to pick safely any size for that area, and we would be fine. So let's write it again. 2E is equal to Q over A divided by epsilon naught. And if you ever get confused with fraction bars over fraction bars, let me teach you a small trick that my high school algebra teacher taught me. That is to multiply this whole thing by a clever form of 1. In this case, our clever form of 1 is 1 over epsilon naught divided by 1 over epsilon naught. You'll notice that this epsilon naught basically turns into 1 with this epsilon naught. And then now we can look at where this epsilon naught is going to land in our fraction bar. It's going to be underneath that fraction bar. So now we can rewrite it. Let's say 2e is equal to q over a epsilon naught. And we have one more step, which is to get that 2 over to the other side. And we can say that the electric field at some distance above the surface is equal to q over 2a epsilon naught. You notice that one thing is missing from that equation, our distance d from the surface. What does this tell us? It tells us that the electric field above a plane is uniform. It's constant. It doesn't actually matter how far above the surface is. You're going to get the same electric field. And that actually ends up being pretty important when you start digging into capacitors later. But for now, you have an equation that describes the electric field at some distance above a plate of charge. I'd like you to finish the assignment and come to me if you have any questions. And I apologize that this lab has been completely on a whiteboard. In retribution for that, I give you a cat. Thank you, and I'll see you next time.